Hi everyone, Bill Ricksecker here, Product Manager at Allied Machine Engineering. Thank you for taking time out of your day to join us. Today we're going to be going through some Superion drill geometries that we've recently unveiled. Kind of a 1,000-foot view for some of you that maybe aren't too familiar with our Superion product line. We actually have special solid carbide drills, reamers, and then we're also into the PCD and CBN as well. So we have some PCD reamers, PCD drills, PCD end mills, and actually routers as well. And if you're interested in learning a little bit more about the Superion product line, you can go to www.alliedmachine.com/Superion to learn a little bit more about that. So basically today what we're going to do is we're going to go through a few of the new geometries. We're going to go into our HPS geometry, and we're going to go into the HPF, and then also our other geometry, the HP106 as well. So what I'm going to do is I'm going to go ahead and start off by talking about our catalog that we recently released. It's a technical catalog, so you can see it now. It's actually popped up. So what we did was we actually took the geometries and put it into a speed and feed chart. What that's going to do is it's going to allow you to know, depending on what material you're in, what you're typically going to see from the Superion drill with the geometry. So if you point your attention over to the side, there's a special geometry section, and what that is, it's going to tell you if you're in a certain application, what's going to work best for you. So you see on the right side, it actually says the HPM2M for this one, and if you point your attention down at the bottom, it's going to tell you if you're using that HPM2M, that's going to be for 8 times D and over. So we've kind of done the work to say, hey, in a certain application, what's going to work best for you? And that's kind of what we're looking for from Superion product line. Because it is special, these tools are more or less tailored to meet your application. So we want to make sure that wherever you are in whatever material, the tool that we provide you is going to perform the best. At the bottom, you can also notice that there's some reductions for length times D. And then on the right side, it's going to go ahead and give you some options as far as parameters if you're running a step drill or any kind of form or anything that you're using with the Superion line. As we move forward, so we're going to go ahead and go into the actual geometry itself. So the first geometry that we're going to get into is the HPS geometry. So for this geometry, you're going to see more of a radius cutting edge, and that's going to be for improved chip forming. This tool also has a cam ground clearance, and that's for added point strength and stability. This also has an OD flute edge prep, and that's going to be for added corner strength in those harder steels. So kind of as I just pointed out, it's going to be ideal for the harder steels, the high temp alloys, and the harder stainless as well. What we recommend for this drill is going to be our AM420 coating. So you can actually utilize the Allied Machine coatings for these drill geometries as well. What I'm going to go ahead and do is just kind of give you a close-up view of the actual drill. So I'm going to go ahead and step over here. Okay, so you can see that now. You can see on the point here, you can see the radius cutting edge. I'm going to grab my pointer and try to point at it for you. So there's kind of the radius cutting edge that I'm talking about. And then you can kind of see on the top here, that's going to be that cam ground clearance up at the top. So just a kind of a close-up view. So what we're going to go ahead and do now is I'm going to go ahead and actually switch it over to Rob Brown, who's one of our engineer trainers, and he's going to go ahead and walk you through the first live demo that we're going to go ahead and do. So I'll go ahead and introduce him now. Rob Brown.
Thanks, Bill. So as he said, we're going to be running the HPS geometry to start off with. For those of you who don't know me, I'm Rob Brown. I'm the engineering trainer here at Allied, and we're going to be running today on our Kitamura vertical machining center. It's a 30 horsepower machine with a 10,000 RPM spindle, and we're going to have the coolant set at about 650 psi. These are relatively small tools, so we're going to put a bit of pressure behind them so we get some flow. So the first application we're going to be running is the HPS geometry that Bill just showed you. It's a helically fluted solid carbide twist drill with AM420 coating on it. The diameter of the tool we're going to be running is a 10 millimeter diameter. We're going to be going about 1.5 inches deep. The 10 millimeter is about 394 thou in diameter. The depth is going to be 38.1 millimeters or 1.5 inches deep. Speed and feed we're going to run is 200 surface feet a minute, which is just about 61 meters a minute in velocity. And a feed rate of 7 thou per rev, or 0.18 inches a minute. That's going to result in, about just under, right around 13.5 inches a minute, or 344 millimeters per minute penetration rate. Once again, the material is going to be 304 stainless steel, hardness about 160-ish Bernal. So it's relatively soft stainless steel. And my buddy Dave's ready to go here. We're going to get things ready and run this demo for you here. I believe we're going to run a 4-hole pattern. Once again, the machine is a Kitamura mice center, 30 horsepower vertical machining center, 10,000 RPM spindle, coolant set at 650 PSI, or 44.8 bar. So Dave, are you ready? All right, let's go ahead and run this. And we're going to gather up the chips and take a look at them underneath the big screen here. So while this is running, I'll let you know what the load meter runs. The load is about 9% as it's doing its cut. And you can hear it's a nice quiet cut, consistent sound. It's not packing chips in any way, shape, or form. It's still at a 9% load. Everything's running the way it should be. And once again, at that 200 surface feet, this diameter, that RPM is about 1940 RPM. And it's going to run about 13.5 inches a minute penetration rate. So once he gets this done, we're going to gather up some of the chips and take a look at them, see what they look like. And we'll go from there. So I think we're on our last hole, so there we go. So let's open that up and take a look at it and see what's going on. We grab a napkin here. Once again, that ran at 9% on the spindle load. Dave's magnet's not going to work too good here. This 304 is non-magnetic, of course. So, my little funny joke for the day. It made me laugh anyway. There you go. Thank you, sir. So let's take a look at what we get here. So once again, this is running the HPF Geometry at 200 surface feet a minute, 7 thou per rev. Grab my little pointer here so you don't see my fingers in there. This is our entry stringer. So that's going to be expected, and the more elastic the material is, the more of an entry stringer you're going to see. Let me get this kind of moved over here so you can see it. There you go. That's a little bit better. So you can see that entry stringer, and once again, since the material is fairly elastic, you're going to get that. But if you look at the rest of the chips that we made, the rest of the chip form is quite good. And as we know, 304 stainless can be a little bit finicky at some point in time. This made a nice little small chip. It evacuated real nice. The spindle load was even from the beginning of the cut to the end of the cut, which is the way that we want it to be. So that was pretty good, I think. So Bill, why don't you come on back in here, and we can get set up and ready to talk about the next one.
Okay, right. Awesome. Thank you, Rob. So we're going to go ahead and move forward here. The next geometry, excuse me, that we're going to be running is actually going to be our HP 106 geometry. This geometry has an optimized core, point, and web features, and that's going to be for increased strength. The single margin design, and it has a straight flute on this one, so it's a little bit different from that HPS that we just ran. And this is going to be ideal for hardened steels and wear plates. AM 420 coated as well, and that's going to be for enhanced heat thresholds and tool life. And before I move over to the screen, one thing I did also wanted to point out was, what I kind of touched on in the beginning is that since these are the special solid carbide drills, and I had mentioned that they're more tailored for your application needs, when we look at these different applications with these geometries, we actually have some set edge preps as well that we typically would use depending on your application. If you can use the same speeds and feeds that we're offering on our new catalog technical information, we'll use those edge preps, but we can also change it up if we need to depending on your machine, your application, and what it can kind of handle. So I did want to just point that out. I kind of missed that at the beginning. So I'm going to go ahead and scoot over here and show you the HP 106 up close. You guys can see that now. So as I said, this is more of it's a straight flute. It's got that tough center up at the top, and that's going to be for these hardened steels. It's going to help you keep the integrity of the tool, being able to get through it. We're going to go through some harder steel in this next demo, so you'll get to see this thing running through it. We found that it's done extremely well, up to 55 Rockwell. That's what we're recommending it for. but you know, there's some applications out there depending on how you're running it. You know, we've seen it perform up to 60 Rockwell. So this is a great tool, great geometry to use in some of those harder steels that maybe in the past you haven't been able to perform well using it. So okay, what I'm going to do now is I'm going to go ahead and point this back over to Rob, and we will go ahead and run this HP 106.
All right, thanks, Bill.
Yep.
Let me get into camera range here. All right, so to kind of set the table for this one here, for the next demo, we're going to be running that HP 106 drill. It's also coated with the AM420 coating. The big difference with this one is it's a straight fluted tool versus a helically fluted tool like what we ran for the HPS, and it does have different geometry on it as well. So the material we're going to be doing for this demo is going to be H13 tool steel that's heat treated to in the low to mid 40s in Rockwell. Still staying with that 10 millimeter diameter or 394 in inch size, going 1.5 inches deep or 38.1 millimeters deep. Speed and feed we're going to run for this one is going to be a bit slower because of the hardness of the material. So we're going to run 140 surface feet per minute, 4 thou per rev in metric. That is about 42.5 meters a minute velocity. Feed rate of 0.1 millimeters per rev. So it's going to come out to about 5.5 inches a minute or about 137 millimeters per minute penetration rate. We still have the coolant set at that 650 psi or 44.8 bar. And Dave, are we ready for this one? Okay, so with this one we're also going to run a 4-hole pattern. So just like we did before, we're going to run the tool. I'll let you know what the load meter is while it's running. We'll gather up some of the chips when we're done, take a look at them under the big screen here so we can see what's going on. Dave, let's go ahead and do this. So here we go. So that RPM is about 1,360 RPM. And it looks like as it's running, it's about a steady 15% spindle load on the machine. So not taxing it in any way, shape, or form. Everything seems to be running pretty good. As you notice by the video, you can see that the coolant's coming out well. Chips are forming well. It sounds actually nice and quiet. We're not getting a lot of noise out of this at all. There's no sort of chirp or anything else. Now, granted, this is a little bit slower in getting through there, but once again, you're talking about material that's about can get upwards of 45 Rockwell in hardness, so it's not going to go fast. It never does. But the tool works nice and quiet. That load meter stays at a nice, steady, still right at 15%, not bouncing around at all. Sounds good. Coolant's coming out well, so we know that we got good coolant flow through there. Keep those chips moving. And if you notice on the workpiece, there aren't a bunch of chips just laying on top there because the coolant is exhausting the chip rather well and kind of throwing it all over the place. Now what we should see with the chip form on this is it's going to be really small chips because of the hardness of that material, because it's going to break a chip relatively quickly because there's not a lot of elasticity in it based on the fact that it's a 45 Rockwell. So that's our last hole. So let's take a look at what the chips look like. I'll let Dave get these gathered up and we'll take a look at them and see what's going on here. Like I said, the chip form on this is really small. So trying to gather these things up is going to take a second here because we got so many small little chips to deal with. And they're relatively sharp, so Dave's got to put them into a napkin because otherwise he's going to cut his ladylike fingers. All right, so let's go take a look at this. Thank you, sir. All right, so here we go. So here's the chip form that we get in that H13 material. Like I said, this stuff is almost 45 Rockwell. So comparing that to like what we saw with the stainless steel, let me just kind of hold that over top here. You can see that you get a nice normal chip form out of the stainless because you're getting those cone-shaped chips that you would expect to see, but that has a lot more elasticity than this material does. So you can see that you're getting these nice small little chips with that coolant flow that we had through the tool. It made a really nice chip evacuation because the chips were small and easy to evacuate. Everything went rather well. So Bill, come on back. And we're going to get ready to talk about the next video, right?
Yes, so, and kind of what Rob just pointed out as well, and kind of when I was going through the geometry, I mean, you really notice with this HP 106, it's got that straight cutting edge on it. We wanted to put as much strength at that point as we could when you're going into those harder steels. Chip formation typically isn't a big issue with those, so we just want to make sure that it's strong enough. Still got to be able to make a chip, get the chip out of the hole. Using that straight fluid is definitely going to help with that, getting the chips out when they're being made. And kind of with that stainless, when we were running that HPS in there, It had more of that radius cutting edge. It's going to help you with that chip formation, but it was also strong at the point when you're going into those stainless steels, still having the integrity of the drill itself. So I'm going to go ahead and move forward. So our last geometry that we're going to go through today is actually the HPF geometry. So this geometry is a unique open geometry for high penetration rates, specifically tailored for aluminum. So full engagement of all four margins at entry. That's going to help you with stability in the hole. It has a reduced helix angle for increased chip evacuation. So when you're going in those aluminum and you're really, your penetration rate's high, you got to focus on getting those chips out of the hole. You don't want to scar up the hole when it's going down in there. You want to make sure the surface finish is still acceptable for maybe your next operation after the hole is drilled itself. It also has an enhanced tool surface finish to improve chip flow and reduce buildup edge. So we actually polish this flute, and when we polish it, it's going to help you to where that buildup edge won't build up onto that coating that we put on. So we'll polish it after the coating. And then also, again, just helping get those chips out of the hole. You want to make sure that whenever you're pushing it as hard as you are, if you get that build-up chip at the bottom of the hole, that's where you're going to see that breakage, even in aluminum. So high lubricity TICN, that's going to be used for cast and route aluminum. So I'm going to go ahead and step over here and show this drill. So you can see, you can notice the polish on this thing. It's an extremely shiny drill, looks really good. You can see up at the top, it's got the gash up here is have a little bit more of a radius on it. We still need to make sure with this cutting edge that it's still strong enough to be able to push it through the aluminum and see the penetration rates that we're looking for. You can notice here it's got the double margin going through as well. So I'm going to go ahead and step back over. Good with that. So now I'm going to go ahead and point it back over to Rob. We're going to go ahead and run this drill in our aluminum. And don't blink, it's running pretty fast. We want to be able to gain the penetration rates that are needed in these aluminum applications. So, Rob?
All right. Okay, so what we're going to run in this one is going to be that HPF drill that he just was talking about. The coating on this is going to be TICN because the AM420 coating that we run in the other applications has a bit of aluminum in it, so we want to run a coating that isn't going to have any worries of having a marrying of the material. So just to kind of let you know what it is we're going to be running for this third demo, this material is T356, so it's a cast aluminum. It's somewhere around 70 Bernal in hardness. Once again, we're still doing a 10 millimeter diameter, which is 394 an inch, inch and a half deep or 38.1 millimeters deep, speed of 950 surface feet per minute, 14.5 thou per rev, which in metric is 289 meters a minute and 0.37 millimeters per rev. That's the reason why we're running on this machine today, because we need a 10,000 RPM spindle to get us there, because we're actually going to be running about 9,200 RPM. The coolant on this is still set at 650 PSI or about 44.8 bar. After we run this, we'll take a look at the chips. I'll let you know what the load meter is. As Bill pointed out a second ago, this thing's going to run pretty quick. So these 4 holes are going to go relatively quickly. Once we're done with showing you the chips though, we do have the material that we ran, the stainless, the hardened steel, and we'll get the piece of aluminum out so we can take a look at what the hole quality is after we're all done with this. So Dave, if you're ready, let's go ahead and run this aluminum. So once again, 10 millimeter diameter going an inch and a half deep, 950 surface feet a minute, 14.5 thou per rev. For our friends that live in metric land, that's 10 millimeters diameter, 38.1 millimeters deep, 289 meters a minute, 0.37 millimeters per revolution. So let's take a look at what this does. All right. So as I said, this is going to go pretty quick. And let's see, when it's running, it's about 66%. It goes so quick, it's kind of hard to get a really good read on it, but it was somewhere right around in that range. So let's gather up and take a look at some of the chips. And once again, once we're done looking at the chips, we'll get the parts and take a look at those so you can see what the quality of the hole is. The chip form on this, from taking a look at it while Dave's gathering them up here, is very, very similar to what we saw with that H13 material, with that HB106 geometry. It's a very small chip that it creates, which is good based on the penetration rate we're running. We got to keep those chips moving. So making them nice and small makes them easier to evacuate. So let's take a look at what we got going on here. So here we go. Kind of get it centered in the picture here so you can see it a little bit better. And you can see this is a chip form that we get. So once again, it's very similar to what we saw with that HB106 running through the H13. It's a nice small chip. Doesn't have a terrible amount of like heavy deformation. 356 tends to be a good chipping material as far as aluminum goes anyway, but this makes a really good chip. And you know, the thing to remember with that T356 material is it is high silicon aluminum. It's got about 9% silicon in it or somewhere in that neighborhood, so it's quite abrasive. So that's why you're going to need that carbide tool to keep it running. So while Dave's getting that situated, let me grab the piece of 304 stainless. We'll take a look at that underneath the camera here. So here we go. So this was as soon as I figured out how to center this, there we go. So this was the first batch of holes that we ran. This was the one that we did with the, was that the HPS?
Yes.
Is that right? For the first one? There we go. So once again, 10 millimeter hole. You can see, let me see if I can get this tilted around so you can see the quality of the finish. It looks pretty good. There's not a lot of deep gouges or anything like that. And based on the chip form that we saw, not really a big surprise. I'm going to flip it over here. The exit burr on it is quite small. Kind of tilted up here so you can see. I mean, there's a little bit of an exit burr, but I mean, you can barely even feel it. So that came out really, really well. Let me come over here and I'm going to grab a piece of H13 while Dave's marking up which one of those aluminum parts we did. So this was the second cut that we made. This is that H13. It's about 45 Rockwell. So you can see the finish on this is really, really good. But once again, based on that hardness of the material and the fact that we're getting a really clean cut out of it, you can see that makes a really good quality hole. Taking a look at on the back side of it, the burr on it is no bigger than what we got with the aluminum. There's really nothing to catch your fingers on. You can see that it's very, very, very small. So surface finish is good, chip was good, exit burr is good. Let me grab the piece of 356 aluminum here real quick. We'll show you that one. Okay, so here we go. The ones that have these ones right here are the 4 holes that we just did. Once again, you remember how quickly that went. So, I mean, the penetration rate on it was 133 inches a minute, or almost 4 meters a minute, or 3.3 meters a minute. Okay, so you can see the finish looks pretty good. And we didn't actually drill through on this one, so I can't flip that over for you because the part's thicker than the drill is. But the surface finish looks pretty nice. So all in all, the drill performed quite well in all the different applications that we ran. We ran 3 different geometries here. Bill, come on back in here so we can kind of talk about this a little bit. So with the tools that we have, we've got different geometries that we ran, different coatings. You know, with the aluminum we ran the TICN, with the other ones we ran the 420 coating. So what we're aiming for here is good penetration rate, good finish, good chip form, long tool life. I mean, if you can achieve that, then I think you kind of met the mark here.
Absolutely, yeah. So I mean, you know, kind of what I've noted in the beginning of it, you know, these are special solid carbide drills. We ran a lot of them with no steps today, but you know, the big thing is looking at these applications and saying, hey, you know, because it's a special tool, what can we combine? We wanted to make sure that these geometries would perform at the highest level for when we're going into these applications and we're looking at these different maybe operations that we combine. We knew the point of the drill was going to be able to stand up to any test that we had. So definitely high penetration, tool life, you know, basically whatever we're looking at to kind of solve for the customer, you know, that's what we're after, and that was the testing that we put into it behind the scenes before releasing it.
Yeah. Yeah, go ahead.
No, you're fine. No, you go ahead. I was just going to say I'm going to go ahead and move on to the next slide as well.
All right.
And just get that
well,
ready.
I'm going to move out of the way because there ain't enough room for both of us on the screen here.
Okay, awesome. Okay, awesome. Thanks, Rob. So just give it a second. Okay, so what I wanted to touch on quickly here at the end was that on alliedmachine.com, there's a Superion quote form. And this quote form, excuse me, down at the bottom, you can see it there, alliedmachine.com/Superion quote form. So what this is it's more of an application form. This is going to help us understand, you know, what do you have going on, what's the application that you're wanting us to look at, and there's also a section on there for objective, right? So we want to understand as a tool supplier, what issue are we trying to solve? There's got to be an issue for us to come in there and look at, whether that's penetration rate, tool life, you know, even delivery, anything that we can kind of come in there and help you out with. I think as a distributor, as an end user, you know, there's always something that we can do to kind of help, and that's what with Allied kind of moving on, or coming up with this Superion, taking it on and offering it as a product. It's something that we definitely want to add to our plethora with solid carbide and PCD. And then also just being able to utilize the special geometries that we've come up with. I think it's all important, and if you go onto our website and you do log on and see this quote form, you can send it to the App Engineering email, or you can also send it to your local FSC if you have a contact and you know who it is. So I'm going to go ahead and cut out of that. So basically, you know, that's what we have today. I appreciate you tuning in with us and joining us to see these new geometries. There's several more geometries that are online, so make sure that you do go on to that alliedmachine.com/Superion and check them out. As I said, PCD, CBN, and Carbide as well. So thank you for joining us, and hope to see you next time. Thank you.